Hello everyone. In this video, I'll talk about surface plasmon resonance. But before shifting to the actual mechanism of SPR, I really want to briefly overview the plasmon and how does plasmon mean and what is the actual meaning behind this plasmon. Once you understand this plasmon, then it's easier for you to grasp the actual original meaning of the SPR and its structure and how's the purpose of this SPR. So let's go ahead and get started. So what is the plasmon? So they say plasmon is the collective oscillation of electrons when you apply some kind of energy to the system. Collective oscillation of electrons. Well, what kind of energy you may apply? So typically they apply electromagnetic energy. So what is electromagnetic energy? It's basically a light. So when you apply a light, so the electrons, they collectively start oscillating. So how does it work? So let's say we have a metal. We have here a metal. Silver, aluminum, gold, any metal. So what does metal have? Metal has typically loose electrons in the outer shell. So there is a lot of electrons, and they also called conductive electrons on the surface. So what happens when you apply a right amount of energy, which is the right amount of wavelengths or frequency, they start wiggling, they start oscillating. So, and they don't like typically oscillate one by one. They start collectively oscillate when you apply some kind of energy to the system. So I'll just say here, energy. So it's pretty easy. So plasmon is basically the collective oscillation of electrons when you apply an external energy to it. It's not very complicated. So they just start. So the only the requirement here is, of course, there should be a right amount of energy. You can't just apply any energy there and expect their collective behavior, expect the change in their oscillation. So that's what typically plasmon is. So one more thing you really need to understand is a total internal reflection. So I'll just right here, this is just the definition of plasmon. And then next I want to talk about total internal reflection. I dropped the link down below in the comment section where I am talking about total internal reflection and more in details. But here I also go through quickly what it is and how it works, because you really need to understand what is total internal reflection before going to the SPR, before studying the SPR. So what is total internal reflection? A total internal reflection, it's the phenomena they use in physics and optics when the light is completely reflected. So it's by name, it means there is no any light escape. So it's completely reflecting when it hits when the light hits the two medium. Let's say we have a glass here. Glass or prism. So what happens is, so here is there are two medium. So this is a glass medium. And also we have here an air. An air is also medium. So what happens is when you apply a light at a certain critical, at a certain angle, we call it above the critical angle. So what happens is, so the light goes, it hits the, light goes, and the light hits the medium like that. So it's a normal behavior. So you apply a laser or any light. So what happens is it hits the the surface, and then happens is it completely reflects back. So this is basically a total internal reflection. So there should be two medium here. In our case, this is glass medium, and then on top, that's an air. So in total internal reflection, it's not really a rocket science, but one more thing happens. So what happens is, in the total internal reflection, there is going to be some additional energy that generates, some additional electromagnetic radiation. That's what we call evanescent light. So what happens, a very, very small portion of this light, it escapes this surface like that. So it escapes. Not this light. The actual light is coming back, not the incident light, but there is additional light it generates. So you can't see this. That's why we call it wave. It's not really a light. But this is also electromagnetic wave. So there is a specific name for that. This is called evanescent. I apologize if I'm spelling it wrong, but this wave is the evanescent wave. So typically they use it because they say it's a non-propagating wave. So that means it's not like this, that like a light, it propagates. So it exponentially decays. What does it mean is it starts strong, and then it slowly, and it decays. It starts strong, and then it slowly decays. And the scientists really using that to excite the molecule. So the people, the scientists, the chemists and physicists, they came up with the idea to use actually that evanescent field for to excite the molecule for spectroscopy analysis. This is very genius. They're using that. So that's what we call total internal reflection and evanescent wave. So we covered plasmon, we covered total internal reflection, and now let's take a look at actually surface plasmon resonance and what does it mean and how does it work. So let's take a look at the mechanism of SPR, which is surface plasmon resonance, and how does it work, and step by step cover each of the components. So the main part of the SPR is of course the thin metal, might be aluminum or gold or silver, depending on the experiment they are performing. So and the metal, thin metal, there is a prism attached. So now why is the prism? Just because to generate this total internal reflection and to generate this evanescent field. So that's why we need this prism here. So now what we do, we shoot the light, the electromagnetic radiation, and then it internally reflects, it totally reflects the light, and then what happens, it generates this evanescent field. So this is the typical mechanism. And on the other side here, now we can immobilize our biological sample. Typically, they immobilize the antibody, for example, to observe the antibody-analyte or antibody-antigen interaction. So what happens is, so before coupling antibody with any analyte, so they check the reflectivity. They check the intensity. So what happens is when it generates on the screen, you can see a curve. Typically, it's a wavelength versus reflection or intensity. It's typically intensity. So I just write I. So what happens is you can see a curve on the line on the graph. So you can see some kind of curve. There you go. So this kind of curves appear. So that is corresponding to the reflectivity of the system. So because what happens is that it generates this evanescent field. So evanescent field is again non-propagating. It will generate like this. And then it somehow it changed a little bit the refraction, and then what does it do? This is gonna change a little bit the intensity of the light. So it is without touching anything. So you first need to measure the intensity without attaching any analyte. So now what happens? Now we apply analyte. Typically this system, sometimes it's built in a microfluidic system. So where what we have is the other side is, this is the medium, and there might be a buffer or water or something. So now you flush it, and then what happens is there's going to be a analyte, and they attach on this antibody. So they couple it biologically. And now what happens? So here is a very, very important, this part. So what does this evanescent field do, first of all? The evanescent field is not gonna, of course, interact with this biological sample. So it's not really a use because it's just a light. It's not really affecting it. So evanescent field is gonna excite the electrons, and then they can cause this plasmon, cause the collective oscillation of the electrons on this metal surface. So that's what happens. It collectively oscillates those electrons. So that's why we need this evanescent field, because on the thin metal we have here lots of electrons. So E, 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 E. So a lot of electrons on the surface, and when we apply the evanescent field is going, we're not applying evanescent field, we apply the incident light that will generate the evanescent field. The evanescent field is starting causing this plasmon to collectively oscillate those electrons. So now what does electrons do? Are those electrons going to interact with antibody antigen? No. They're not going to interact. So what happens is you're getting the information of the refractive index. So when this analyte is going to attach to the antibody, it is going to increase the refractive index on the metal, on this the medium. So that will affect the radiation that's coming back. So now this evanescent field is no longer the same evanescent field that was in the beginning, that was just where was antibody there. A change of refractive index is slightly changed the reflectivity of the light. So when does it do it? So you can see a slightly shift on the intensity, on the wavelengths. So slightly it shifts. When the curve, you can see shift. From there, you can identify, can find out how much analyte, or can see the interaction between analyte, and you can also calculate the kinetics of your analysis. So that's the kind of information you will get. So the electrons and evanescent field, the metal, they're not going to interact with the antibody and biology itself, but what they do when you attach the antigen there or the analyte, now it's going to change the refractive index. When your refractive index changes, so how do you know the refractive index changed? This is the only way to know the change of the refractive index. It's when you apply the total internal reflection. Now reflected light is not going to be the same as it was before the analyte was there. So this is how the surface plasmon resonance works.